So now that we understand IP version 4 addressing schemas and what the header looks like, let's pivot and start talking about how our network's created, how do we define the scope and size of a network, and what are the key elements of information we'd like to extract to help identify the scope and size of a network. So we talked about IP addresses having general classes or sizes and ranges, but we need a better way to manage the size of our networks. So imagine if you're given a pizza, you need to make the most efficient use of that pizza if you have more than 8 guests. You need to cut up some of those slices so that everybody can get a piece. And that's what subnetting is all about. It's about defining the size of networks to your needs so that you're not wasting addressing, but you're also using just enough to provide enough IPs for your use case. When given an IP address, the way we help determine the size or scope of the network that address is communicating from, we usually receive a subnet mask. It is a corroborated address that looks very similar to an IP address, but it is used to compare and contrast what portion of the address belongs to the network and what belongs to the host portion of the address. So by doing a little math with the subnet and the given IP address, we can identify the network ID, which is the ID used to identify a network, the first available IP address, the last address, and the broadcast address used within that network. So one way to think about what a network ID is you could think of a network ID as a street. If you live in a town and I say go to Elm Street, hopefully we don't find Freddy Krueger, but if we go to Elm Street, we all know where that is. So that would be considered like a network ID. It is the portion of the IP address that says, hey, to get packets to that network, it's generally over here. We know how to get there. The host portion, which constitutes the first through last address ranges, which can actually be applied to the devices on that network, think of those in relation to Elm Street, and the host addresses are the unique address numbers of the houses on that street. So 22 Elm Street is the network ID Elm Street, and 22 being that host address or home address. So that's how we would use a network ID to get to the general vicinity of where a network is, and then we use the first through last address that are assigned to a device to know specifically where to send the data. And again, if you recall, a broadcast address is the address that's used to do an all-net broadcast communication. And that is actually an IP address that is configured for that network. A broadcast is not an IP address that your device has on it. It's one that it uses to communicate with. It assumes that broadcast identity to communicate on the network. So to get prepared for subnetting, we need to do a little bit of conversion or subnetting math. And one of the key things we need to understand is how to calculate a base 10 value from a base 2 number or binary bit of data. And remember, we always want to think about those 1 bits as being the on values. And in this example, we want to count or calculate or sum every value that corresponds to a 1 bit being on. Before we get into that, though, we need to look at what makes up binary data. So we can see that we have a number in the top row counting from 128 on down. Well, this is 8 bits. And if you remember, an IP address is 8 bits per octet, right? We have 4 octets, 4 groups of 8. So when you look at 8 bits, because it's binary, you multiply and you count by 2s, beginning from 1 on the right, 1, 2, 4, 8, 16, 32, 64, 128. You could keep going. 256, 512, 1024, 2048, 4096, so on and so forth. That's the benefit of binary. If you can count by 2s, you can do binary math really fast. So the way we convert a binary number, 1s and 0s, into a decimal number is we line up the binary value with its positional value. So we can see the positional values, 128, 64, 32, and so forth. And below we have the binary value. So all we're doing is simply counting up. Whenever there is a 1, we count that value. So whenever we think about computers calculating 1s and 0s, what they're actually doing is they're referencing the placeholder value of that 1 or 0 in relation to the overall binary string that's being processed. It's not like we're sending 1s and 0s that initially or by themselves equate to something. They have correlated base 10 values that are being calculated. That way, we can use a few ones and zeros to calculate very large numbers quickly. So in this example, every position that had a 1 was on, and we simply grab those values. So we have 128 plus 32 plus 8 plus 4 plus 1, which equals the base 10 value of 173. So that binary string 10101101 actually equates to the value 173 in base 10. This is how we can convert a binary string to a base 10 string. Conversely, we can convert a base 10 number into a binary number. So if we had this base 10 number of 173, the way we would convert it to binary is when we start looking at the available bits here, you start deducing which numbers fit within 173. So does 128 fit within 173? Yes, it does. So we turn that bit value on. It is smaller than 173. Is 128 plus 64 greater or smaller than 173? Well, it's greater. So 128 and 64 won't work. But is 128 and 32 smaller than 173? It is. So, okay, 128 is on and 32 is on. And we keep doing that until we get to the final value that equates to the same number. So we're moving pretty fast here, but let's look at a subnetting example. Let's bring a lot of these concepts together we just talked about. So the first thing we want to do is we need to convert that base 10 IP address to base 2. We want to go from a normal base 10 address to that binary address. So we can see in the first row, we have the base 10 values, 10.10.10.5, that's an IP address. And we've converted it to binary, seen below. So 00001010, that's 10. And we can see we have that 3 times because that's how you calculate 10 in binary. And then the last octet is 00001001. That's how you count up to 5 in binary. So here's the first time we've really looked at a subnet mask. So a subnet mask is used to essentially carve out or to say this portion of the network belongs to the network and the remaining portion belongs to the hosts. You can do whatever you want with the host bits, but the network is static because that is used, right, to get us to that Elm Street. We can't change Elm Street. We can't move it to another road. It has to be static. So that's what we use subnet masking for, is to help us initially identify the network ID. So we need to convert that subnet mask to base 2 just as well. So we can see here 255 is the maximum value in an octet if you turn all the ones on. So 255 in binary is all ones. And then we can see a 0 in base 10 converted to binary is all zeros. So I hope you're starting to see here that by having all the ones on, we're simply saying these first 3 octets, that's a portion of the network ID. So 10.10.10 is a part of the network ID. It's not the full network ID yet, but it's the network ID thus far. So next what we do is called a logical AND, and this sort of brings back the little bit of binary math we did before. And the goal here is if we look at the IP address base 2 row and the subnet mask base 2 row, we're simply comparing the 2 rows. And when we look at the subnet, wherever there is a 1, that is simply the address that we're keeping. We're going to let it pass through. So a good way to think about this is that a 1 is always considered on or true, and a 0 is considered off. And we've got to think about it in the way computers work. Computers are just advanced wires that calculate ones and zeros through switches or gates that are just turning on and off. So if you think about binary and put that in relationship to a tunnel that you want to drive through, and each side of the tunnel has a gate that's going to open or close, if both gates are set to 1, they're going to open. You can drive through the tunnel. But if there is a 0 on either side, you obviously can't get through. If the door closest to you is set to 0, you can't go through it. But if it's set to 0 on the other side, you might be able to start driving through, but you're still going to be blocked. You can't get through. So in this example, whenever we have a 0, that logic gate is closed. We can't use it. It isn't valid. Don't move further. So this is what we do by logical ANDing. We're looking at the base 10 IP address in base 2, and we're looking at that subnet in base 2, and we're saying, hey, the subnet is telling us which portion of the IP it's going to keep for itself. Remember that it's going to keep that portion for the network ID. So we quickly go in here and say, well, they're all ones turned on in this first portion of the subnet mask binary. So that means anything in the IP address base 2 address belongs to it. So again, you could see in that sort of yellow row that the same 10 value in binary falls through. And we see that for these first 3 octets. So this subnet mask of 255.255.255, or all ones, is essentially saying the portion of the address 10.10.10 belongs to the network. And then last but not least, we have these zeros on the end here. Well, zeros means it's off. We're not going to be calculating that. Do not pass go, do not collect $200. So the network doesn't own that portion of the IP range because it's all zeros. It's not claiming ownership. So if we were an admin, this is like somebody telling us, look at this big IP address, but you only get the last octet. But you could do whatever you want with that last octet. And that's what a subnet mask is for. So from that subnet mask, we've learned that the network ID is 10.0.0.0. That's how we define what network ID this is, because the subnet mask told us which portion of the range belongs to the network, and the first IP value of the host is used to comprise the overall network ID, that street. So 10.0.0.0. And then we know the first address is because it's just incremented. The first IP address we can use is 10.0.0.1. That's the first IP that we can use in our own network, in the host portion. The last address we can use is 10.0.0.254. And again, that broadcast, 10.0.0.255, the last IP address in the network. So that's one thing I want you to remember, is that a broadcast is always going to be the last IP in a defined network. So even though if you found this confusing, which it's very easy to find confusing, it takes some time to get comfortable with binary math and to calculate this. But at the end of the day, the important thing to remember is that subnet masks are used to define the size of a network to make it more efficient for management purposes. But it's important for us to begin to understand what subnets mean to IP addresses, because it helps us analyze the size of a network. If we're doing reconnaissance for an engagement, if our boss asks us to look at all of these servers in this network, we want to make sure we looked at all of those servers and not looking at servers in another network, right? That's scope creep. What if we were doing a vulnerability scan and we scanned the wrong hosts because we don't understand subnetting and what that means in relation to the size of a network? So this is why it's important to understand subnetting.